So today we are starting a new topic, sequence and series. So write convergence of a sequence so a function f from 1 to 3 and so on, that is from natural numbers to real numbers, is called a sequence of real numbers. And we write f of n as xn. Okay, so our sequence will be, the sequence is denoted by x1, x2, x3 and so on, or simply we will write x and n greater than equal to 1, okay, where xn is the nth term of the sequence. Xn is the nth term of the sequence. Examples of sequence. First one, n is greater than equal to 1, that is 1, 2, 3 and so on. Second, 1 by n greater than equal to 1, that is 1, 1 by 2, 1 by 3, 1 by 4 and so on. Third one, minus 1 raised to the power n by n, that is nothing but minus 1, 1 by 2, minus 1 by 3, 1 by 4, minus 1 by 5 and so on. Fourth example, 1 minus 1 by n, that is equal to 0, 1 minus 1 by 2, 1 minus 1 by 3, 1 minus 1 by 4 and so on. That is 0, 1 by 2, 2 by 3, 3 by 4 and so on. Fifth example, 1 plus 1 by 10 raised to the power n is greater than equal to 1, that is 1 plus 1 by 10, 1 plus 1 by 100, comma 1 plus 1 by 10 cube and so on. So this is nothing but 1.1 plus 1.01, 1.001 and so on. Sixth example, minus 1 raised to the power n is greater than equal to 1, that is minus 1, plus 1, minus 1, plus 1 and so on. Now, convergence of a sequence.
Akash, just show me the fifth sequence, please.
Yeah, fifth.
I was just noting down. Thank you. Thank you, Akash. That's all.
So convergence of a sequence. So first look at the example. Consider the sequence 1 by n greater than equal to 1. Let's plot this on the real line. Consider this as 0, this as 1, then 1 by 2, then 1 by 3, then 1 by 4 and so on, right? Now, you take any neighborhood of 0, any interval around 0. For very great value of n, or for the larger value of n, your sequence will be inside this, right? Inside this neighborhood. No matter how small your neighborhood is, your 1 by n will be inside this interval, right? So then we write limit n tends to infinity, 1 by n is equal to 0. Okay. Now formal definition for that. So for every epsilon greater than 0, there exists a positive integer n depending on epsilon, such that xn belongs to x0 minus epsilon to x0 plus epsilon for all n greater than equal to capital N. Then we say that, so if for all epsilon, then we say that xn converges to x0 as n tends to infinity, or limits n tends to infinity, xn is equal to x0. Okay. Now look at this equation again. This is same as xn is lesser than equal to x0 plus epsilon and greater than equal to x0 minus epsilon. Right? This as xn minus x0 is lesser than epsilon and greater than equal to minus epsilon for all n greater than equal to some capital N. This means that the tail part has to be inside the epsilon neighborhood around x0. So this is same as xn minus x0 modulus lesser than epsilon for all n greater than equal to n. So convergence means you have, wait a second. So x0 here, you are taking a neighborhood of epsilon around this. So this will be x0 plus epsilon. This is x0 minus epsilon. Now your tail part, that is, I don't know what is wrong with my tab today. So x0, then this is x capital N, then something x capital N plus 1 here, x n plus 2 here, maybe x n plus 3 is this one. So tail part has to be inside this neighborhood. That's what convergence means. Okay.
What is the tail part meaning over here?
Tail part I mean by xn, xn, xn plus 1, xn plus 2, xn plus 3, and so on. This I mean by tail parts. Okay. But it will change according to the epsilon, because n depends upon epsilon. Okay.
N depends upon epsilon.
Yes.
How come? Like epsilon is a very small quantity, right?
Yeah, it can be anything. It can be 1, 2, 3, anything. It can be as small as possible, as big as possible.
Okay.
Now let's look at the example again. Let's look at the sequence number 4. 1 minus 1 by n. Okay. Consider xn is equal to 1 minus 1 by n. Now 1 minus xn is equal to 1 by n. Take the modulus. Okay. Now we want this to be lesser than epsilon, right? 1 by n is positive, so I can remove the mode. So 1 by n is lesser than epsilon. That means n is greater than 1 by epsilon, right? So I can choose my capital N to be 1 by epsilon greatest integer plus 1, because I need this to be an integer. Now for n greater than equal to capital N, what happens? Your 1 by n is lesser than epsilon. That means your 1 minus xn modulus is lesser than epsilon for all n greater than equal to capital N. Okay. Is there any doubt here?
Yeah, just show the proof once again.
Yeah.
For example, the series is 1 minus 1 by n, right? So 1 minus xn modulus equal to 1
Yes.
by 1 by n modulus, which is from the equation itself. So
Yes.
1 by n should be less than epsilon, because modulus of 1 by n is less than epsilon. So 1 by n lies between minus epsilon and plus epsilon.
Yeah, these are if and only, by the way. You can go back and forth.
And n greater than 1 by epsilon. Okay.
Yeah.
So capital N, you have set capital N to be a particular value of small n, right?
Yeah, because I need this to be a greatest, I need this to be an integer. So 1 by epsilon may not be an integer, right?
Mm-hmm.
So I am choosing
Are you
a
choosing the ceiling?
integer. Look at here, this is 1 by epsilon, then this will be
Yeah.
1 by epsilon greatest integer, right?
Mm-hmm.
Then plus 1 will be here.
Why then plus 1? If greatest integer is also is giving you an integer, then why are you adding 1?
Because, yeah, you don't need to do that also. It's fine, both are fine. This one and this one.
1 by epsilon is also fine, the greatest integer of 1 by epsilon.
Yeah, that one is also fine, yes. So both will work.
Modulus of 1 minus xn is less than epsilon.
Yes, that means limit x and n tends to infinity is 1.
Limit x tends to infinity, n tends to infinity, xn is 1, which is, so 1 minus xn. Okay, 1 minus xn should be less than minus epsilon plus epsilon.
Yes.
Right. So then, okay, so x. So adding both, I mean subtracting 1 from both the. I mean it will be minus xn between x. Okay, so
Yeah, so
xn, yeah, okay.
let me
X,
extend on.
yeah, sure.
So this is
Yeah.
1 minus xn
Yeah.
modulus lesser than epsilon. Then write this as 1 minus xn lesser than epsilon and greater than minus epsilon.
Correct.
From here you get minus xn is lesser than epsilon minus 1 and greater than minus 1 minus epsilon.
Yes.
But we have minus here, so we will reverse the inequality. That means xn
Yes.
is greater than 1 minus epsilon and lesser than 1 plus epsilon.
Yes.
Or you can flip this, write this in this form, 1 minus epsilon to 1 plus epsilon for all n greater than some capital N.
Correct.
That means you have 1 here, 1 minus epsilon here, and 1 plus, sorry for this, 1 plus epsilon here and your sequence xn for all n greater than equal to capital N will be inside this neighborhood here, in this neighborhood. Okay.
Correct.
And your epsilon was arbitrary. So that means your sequence converges to 1.
So epsilon is a small quantity over here, right?
Yeah. Yeah.
And okay. So limit tends to infinity, xn is equal to 1.
Yeah.
So it converges to 1.
Yes.
Okay, thank you.
Now theorems. Suppose xn tends to x and yn tends to y, then their sum xn plus yn will converge to x plus y. Second, xn into yn will also converge to xy. Third case, xn by yn converges to x by y if y is not equal to 0 and yn is not equal to 0 for all n. Now, next theorem, which is known as the sandwich theorem. So suppose xn, yn, and zn are sequences such that xn is lesser than equal to yn is lesser than equal to zn for all n, and xn converges to x0 and zn converges to also x0, then yn will also converge to x0. Okay. Example, take xn is equal to sine of n by n. Find limits n tends to infinity xn. So think about this question. You have to apply the sandwich theorem. I'm giving you 1 minute to try this. So think about this. Now look at modulus of xn. that is equal to sine n by n modulus. Now this is lesser than equal to 1 by n because sine n modulus is lesser than equal to 1 for all n. Even this is true for every real number also. So that means sine n by n is lesser than 1 by n and greater than equal to minus 1 by n. Now both side limits goes to 0. Your limit n tends to infinity 1 by n is equal to 0 and limit n tends to infinity minus 1 by n is also 0. So which implies by sandwich theorem limit n tends to infinity sine of n by n is 0. Okay. Next question. Take yn is equal to n square by n cube n cube plus n plus 1 plus n square by n cube plus n plus 2 plus up to n square by n cube plus 2 times of n. Now show that limit n tends to infinity yn is equal to 1. Hint. Yn is lesser than equal to n into n square by n cube plus n plus 1 and greater than equal to n into n square by n cube plus 2n. So if you can prove this, then you are done. So take your time and think about this. Matthew, do you have any doubts? Matthew, Binoy?
Akash, can you just share it once again?
Yeah. So if you can prove the hint, then you are done. So think about this.
And
Sir,
Yes.
so can I tell the proof for this hint?
Yeah. Tell me.
Sir, we are taking yn as summation of terms. So if there are if we are saying about yn, then there are n terms,
Yes.
and
Exactly.
each term is of the form n cube plus n plus I times n.
Yeah.
No, not I. Sorry, plus I.
Yeah. Plus
And
I. Yes.
so plus I, and we know that n cube plus 2n will be definitely greater than n cube plus n plus I, where I is not
Yes.
equal to n. So
Yeah.
n
Yeah.
times, so n times of doing n square by n cube plus n plus 1 will be greater than n times of doing n square plus n cube plus 2n.
Yeah. You are right.
So, yes.
So what
so
Subham is
n cube plus 2n n square by n cube plus 2n. This is
Yeah.
this is at
Smallest
most.
one.
This
This
is
is
the
the
smallest one.
smallest. and the first one is your greatest one.
So if we are dividing by n cube plus n plus 1, so that actually increases with the terms, right?
Yeah, exactly. So that's why we have n times of this one.
Oh, okay.
So
No,
let me,
n into whatever is that. So
yes,
that number itself is increasing. The first term is the lowest and the last term is the highest, right?
this one,
Now this is the
this is the
should be
highest, this is the highest one because your
yeah.
because
Numerator
your
is
denominator is increasing.
denominator is increasing. Yeah. Correct.
So 1 by reciprocal of your denominator will decrease at.
Decrease, correct.
Yeah. So let me explain this again. So you look at n cube plus n plus 1. This is lesser than equal to n cube plus n plus k for k greater than equal to 1 and lesser than equal to 2n. Actually, this is true for any k greater than equal to 1, but we are only restricting our case to up to 2n. Okay. And this thing is greater than equal to.
I think Akash, k should be between 1 and n because you have n cube plus n.
Yeah. Thank you
I
for
think-
this. K has to be n. Yes. Because last one is n plus n. Yeah. Thank you.
Yeah, my bad.
So k has to be between 1 and n. Now, the reciprocal of this, that is n cube plus n plus k, is lesser than equal to 1 by n cube plus n plus 1. So, yn is summation n square by n cube plus n plus k. K is from 1 to n. Now this is, each term is lesser than this. So this is summation k is equal to 1 to n, 1 by n cube plus n plus 1. But this is independent of k. So this will be n times of, there will be n square here. So this will be independent of n. This is equal to n into n square by n cube plus n plus 1. That is n cube by n cube plus n plus 1. This is our first one sided. Now for the other side, you write this as n square plus n plus n is greater than equal to n square plus n plus 1. Now 1 by n square plus n plus 1 will be greater than equal to 1 by n square plus n plus n. But I should take k here. K is between 1 and n. So we are done. So yn is equal to summation k is equal to 1 to n, 1 n square by n square plus n plus k. This is greater than equal to n square by n square plus n and n times. So this is n cube by, this is cube in the denominator, right? This is cube here, please correct that. Yeah, so n cube by n cube plus 2n. So that means your yn is lesser than equal to n cube plus n cube by n cube plus. Now yn is lesser than equal to 1 by 1 plus n by n cube plus 1 and greater than equal to 1 by 1 plus 2n by n cube. Now limit n tends to infinity, 1 by 1 plus 2n by
Akash, can you
n.
just scroll up a bit? I just lost you in between.
Yeah.
Just one. Yeah, there's a no, stay here. Stay. No, just scroll down. Just scroll down. N cube plus n plus yeah. Yes. Yeah, n into n square. So this n comes from the summation itself,
Which,
right? This one.
yeah, this n comes
Y
from
and
the
equal
summation. Yes,
summation, right?
because
The
each
same
term
same
inside
stuff.
the summation is independent of n, when you take the inequality.
That means we are independent of k, in fact.
Yeah, independent of k. Yes.
Yeah. So this is greater than equal to n plus n. So n, no, just a second. Yeah, correct. Okay. From the above inequality, yeah.
Yes, this
One
one.
by. Mhm.
This one.
Correct. Yes. Yeah, n cube by n cube plus. Yeah. Just scroll down.
Yeah.
Cube by n cube and one by. Yeah. That. Thank you.
Does anyone else have doubts? So this is limit n tends to infinity 1 by 1 plus 2 by n square. So this will be same as, we will apply this rule now. I wrote the theorems. Look at this third point. Okay. So this is 1 by limit n tends to infinity 1 plus 2 by n square. That is 1 by 1 plus limit 2 times n tends to infinity by 1 by n square. And this is nothing but 1 by 1 plus 2 times 0. That is 1 only. Okay. Now look at for the right hand side, we have limits n tends to infinity 1 by 1 plus n plus 1 by n cube. That is again 1 by limits n tends to infinity 1 plus 1 by n square plus 1 by n cube. This is 1 by 1 plus limits n tends to infinity 1 by n square plus limit n tends to infinity 1 by n cube. And that is nothing but 1 by 1 plus 0 plus 0. This is 1. So your left and right limits are 1. That means by the sandwich theorem, your middle yn will be, limit will be 1. So by sandwich theorem, limit yn n tends to infinity is equal to 1. Okay. Next question. Let x belongs to R and x is greater than 0 and lesser than 1. Show that x raised to the power n tends to 0 as n tends to infinity. So think about this. So let me show this. My x is between 0 and 1. Right, x is equal to 1 by 1 plus a for some a greater than 0, right? 1 plus a is greater than 1. That means 1 by 1 plus a is lesser than 1. Okay, so your x will be lesser than 1. Now x raised to the power n, that is greater than 0, is equal to 1 by 1 plus a raised to the power n. Now write Bernoulli inequality. One plus a raised to the power n is nothing but, does everyone know binomial theorem? Does everyone know binomial theorem?
NC0,
Yeah,
I think that I don't think that NC0 plus NC1 x into
yeah.
1 plus, you're right, yeah, you're giving 1 plus, right? Yeah,
Yeah.
so a to the
So,
power n minus 1.
so this is nothing but NC0 plus NC1 into a plus NC2 into a square plus up to NCn into a raised to the power n. Now a is greater than 0, that means this thing is greater than equal to NC0 plus NC1 into a, and this is nothing but 1 plus n times a. So this is the Bernoulli inequality. 1 plus a raised to the power n is greater than equal to 1 plus na, a is greater than 0. Okay, clear? Now we'll use this. This is greater than.
So it's NC0 plus NC1 a, which is 1 plus na, but you're ignoring the other terms, right?
Yeah, I am removing all the terms because I need greater than. So now 1 by 1 plus a raised to the power n is lesser than equal to 1 by 1 plus n. You reverse this. Now
n is positive, right? A is positive, right?
Yes, a is positive. That's why we are. Now 0 is lesser than x raised to the power n is equal to 1 plus a raised to the power n. This is lesser than equal to 1 by 1 plus n a, and this is lesser than 1 by n a, right? Because 1 plus n a is greater than n a. So if you divide by big number, then your number will be lesser than your original number. Okay. Is it clear, this one? Your 1 plus n a is bigger than n a. So when you divide, your number will become smaller. Now limits n tends to infinity 1 by n a is equal to 1 by a times limits n tends to infinity 1 by n, and that is nothing but 0. Now you have both sides 0, so that means limits n tends to infinity x raised to the power n is 0 by sandwich theorem. Okay. But first of all, does this make sense to you intuitively? You have, let's say, a is your x was between 0 and 1. Let's take some example now. So let's take x is equal to 1 by 10. Now consider x raised to the power n, n is greater than equal to 1. Now this is 1 by 10 raised to the power n, n is greater than equal to 1. Now limits n tends to infinity 1 by 10 raised to the power n is nothing but 0. Because your denominator is keep on increasing and you increase the n. So reciprocal of that will keep on decreasing and will reach 0. Okay. This will happen for any real number between 0 and 1. Next one. These are standard example. You should remember them. Okay. And you should remember their proofs also. These are not just the mere proofs, but just these are techniques involved here. You should remember that we are using Bernoulli inequality here, how we are using it. Okay. You should remember the techniques. Now, next example, let x belongs to real number and x is greater than 0. Now, show that limits n tends to infinity, x raised to the power 1 by n is equal to 1. Now, let me give you the hints. Case 1, when x is greater than 1, then you write x raised to the power 1 by n will be greater than 1. So write this as equal to 1 plus dn for some dn greater than 0. You can find dn, right? This is same as you take dn to be 1 minus x raised to the power 1 by n. Okay. Now, fine. And dn is greater than 0 because dn is, no, I should write the opposite. X raised to the power 1 by n minus 1. Now dn is greater than 0 because x raised to the power 1 by n will be greater than 1 as x is greater than 1. Okay. Dn is greater than 0 as x is greater than 1. You have to use this. And you have to use Bernoulli inequality.
So Akash, x would be
Yes.
equal to 1 plus dn to the power n, right?
Yes. So x is equal to 1 plus dn raised to the power n. Now use Bernoulli inequality. This is greater than 1 plus n times dn because dn is greater than 0.
Yes.
Now this is greater than n times dn, right? Because we are adding 1 in there. Now that means n times of dn is lesser than x. So dn is lesser than x by n and greater than 0. Now use limits right hand side. Limit n tends to infinity x by n is nothing 0 because this is x into limits n tends to infinity x 1 by n. this is equal to 0. So we implies limits n tends to infinity, dn is equal to 0 because we have both sides 0 by the sandwich theorem.
So dn, so dn equal to
Now-
limit n tends to infinity, dn equal to 0.
Yes, but what is your dn? dn is x raised
dn
to the
is
power 1 by n minus.
minus 1.
So
Okay.
dn,
So proof.
yeah. So x raised to the power 1 by n minus 1 is equal to 0. But then this is same as limit n tends to infinity, x raised to the power 1 by n is equal to 1. Clear?
Yes.
Okay. Now case 2. Your other case when x is between 0 and 1, because x is greater than 0, when x is between 0 and 1, then you take y is equal to 1 by x. This will be greater than 1. That means y raised to the power n. I need y raised to the power 1 by n. Y raised to the power 1 by n is equal to 1 by x raised to the power 1 by n, which is 1 by x raised to the power 1 by n. Now y is greater than 1, right? So limits n tends to infinity, y raised to the power 1 by n is equal to limits n tends to infinity 1 by x raised to the power 1 by n, which is same as 1 by limits n tends to infinity x raised to the power 1 by n. Now this is 1 from the previous case. So that means your denominator has to be 1 also. Clear? So we are done with both the cases.
So how do we come to know limit n tends to infinity x to the power 1 by n equal to 1 from the previous case?
No, look at your limits. This one, this box, this is 1, right?
Yes, 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 right.
So
That is
I will write it again. Now we are
that is
getting from
1. Just a second.
1
That
by
is
limit
1.
is equal to 1, right? Now denominator has to be 1. No?
No, that's fine. But how do we get limit n tends to infinity y to the power 1 by n equal to 1?
Because y is greater than 1. Y is 1 by x. X is lesser than 1, but when you take the reciprocal, it will become greater than 1. Now we are using previous case. So from
Okay.
case 1.
Mhm.
Okay.
Okay.
Now
Okay.
fine.
Here it is from case. Yeah. Just
Next example. Find, these are very useful limits. Okay. We will be using these again and again, these results. So find limits n tends to infinity n raised to the power 1 by n. So think about this. We have to use same kind of tricks I used in this case number. Okay. So let's use the same trick again. Write n raised to the power 1 by n as 1 plus dn. Okay. Or you can write dn as n raised to the power 1 by n minus 1. Now n is equal to 1 plus dn raised to the power n. Now apply binomial theorem. So 1 plus, by the way, dn is greater than 0. When n is 1, this is 0, so greater than equal to 0. Doesn't matter, it is still positive. So 1 plus x, when x is greater than equal to 0, raised to the power n is equal to nc0 plus nc1 into x plus nc2 into x square plus up to nx raised to the power n. Okay. Now, this is greater than equal to 1 plus nc2 into x square. Because I have other side as n here. So this time I will take square from the binomial theorem. Let's use this. So n is equal to 1 plus dn raised to the power n.
So here we
This
are
is
not
very-
taking, Akash, here we are not taking the x term.
No, because I have other side as n. I will show it to you why this will be helpful for us.
We have
So-
other side as n. Okay.
Yeah, look at this. So 1 plus nc2 is n into n minus 1 by 2, and we have dn whole square. Now n minus 1 is greater than equal to n into n minus 1 by 2 into dn whole square. Now n minus 1 and n minus 1 will get cancelled, and dn whole square will be lesser than equal to 2 by n. Right, and greater than equal to 0, obviously. Now dn is greater than equal to 0 and lesser than 2 by n under root, but then your limit n tends to infinity, under root 2 by n is same as under root of 2 by limit n tends to infinity of n, that is equal to 0. Okay, because in denominator you have infinity. So that means your limit
dn is by default greater than 0, right? So dn square, oh, dn square is by default greater than 0, sorry.
No, but dn is also greater than 0. Look at here, na? Dn is n raised to the power 1 by n minus 1. So when n is 1, your d1 is 0. Your d2 is 2 raised to the power 1 by 2 minus 1. That is root 2. Root 2 is 1.414 minus 1. So this is 0.414. Your
Increasing.
d3 is 3 raised to the power 1 by 3 minus 1.
Yes.
But then this is 1.73, not 1.73, but
No.
this is still greater than 0.
This is still greater than 0.
Still greater than 0. Yes. So dn is still greater than equal to 0 for all n. So which implies limit n tends to infinity, dn is 0 by sandwich theorem. So now we are done. Now. So dn is nothing but n raised to the power 1 by n minus 1. So limit n tends to infinity, n raised to the power 1 by n is equal to 1. Okay.